in this class, we've looked at one sample sets, and just recently in chapter 7 and chapter 8, we looked at comparing two sample sets. So you would have either an independent or dependent samples, and we would do some analysis on those. We would compare the means of two samples. We compared the proportions of two samples. So we did a lot of stuff with two samples. An ANOVA test compares 3 or more samples. So if you have 3, 4, 5 different samples, 5 different categories, how do you compare their means? And this is what an ANOVA test does. So what it does is it compares the mean and standard deviation across multiple samples. And in order to do this, you create a lot of very complicated mathematical calculations, okay? And so the graphs that you get, we're not talking about a normal distribution. We're not talking about a t-distribution or a z-distribution, a z-score or a t-score or a chi-squared score. We are talking about something completely different. And so that completely different distribution is known as the F distribution. So the F distribution is what you use when you're calculating all these multiple samples, okay? And the graph looks really crazy. Here's just an example of a small sample of F distributions. And you can see finding the area under these curves would be difficult to do. And so we're gonna rely heavily on technology to do this. So when you have an ANOVA test, ANOVA, somebody forgot to put the letter V in there. When you have an ANOVA test, you're going to take your data, you're gonna plug it into a spreadsheet or a website, and it's going to use an F distribution and calculate a p-value, an area under the curve. You're gonna take that p-value, compare it to an alpha, just like we did before, and determine whether or not you should accept or reject the null hypothesis. So the overall concept is exactly the same as what we've been doing the last 2 chapters, right? Here's a hypothesis, here's a null hypothesis. You're gonna look at a p-value, compare it to a threshold, and then determine whether or not you accept or reject the null hypothesis, right? That's what we're doing. So here's the setup. You have to identify your random variables. And so however many sample sets you have, that's what K is. So for example, if you had 5 samples, then you're gonna have X1, X2, X3, X4, X5. So K would equal 5 in this case, okay? For each sample, you're gonna calculate the mean. So for each sample, you calculate the mean. And then this is where you get into the hypothesis testing. So the hypothesis is, the null hypothesis, the accepted hypothesis is that all the samples have identical means, that the mean, the average of all 5 samples is the same. That's your null hypothesis. You go and you take your data, you run some calculations, you get an F distribution, which then gives you a p-value. You compare that p-value to a threshold, and you either accept or reject the null hypothesis. If you accept the null hypothesis, then there's evidence to show that all the samples have the same average, the same mean. If you reject the null hypothesis, then that means at least 2 of the means are not the same, not equal. Okay, so in order to proceed with these calculations, you have to make sure that your samples are random, that they're independent, they're normally distributed, and that the variances are nearly equal. So you want sample sizes that are well behaved, okay? So here is the calculation, and just bear with me on this, okay? You're not gonna have to memorize this, but we've got to explain it so that way you can understand what ingredients are going into this soup that we're making, okay? So here are the ingredients, and we're actually going to start with, this is the F, this is the F distribution score. This is what we're going to find the area under. This is our target, right? This is our target. So when you do your distribution graph, this is going to be F, and you're going to find the area above F, okay? So what goes into F? Well, F is composed of MS sub B and MS sub W. And these things are composed of SSB and degrees of freedom, SSW and degrees of freedom of SSW. So what in the world are these things? So we're just kind of explaining the overall structure, and now let's talk about the ingredients. So what is SSW? So when we talk about these 5 samples, when we talk about within and between, we want to look at within and between. So within looks at the deviation squared of each category and adds them all together. So this would be if you took each sample and found its standard deviation, squared the standard deviation, and then added those all together, okay? That's within. So kind of like each individual column is its own calculation, and then you add them all up, okay? The between is if you took all those categories and just made one giant set out of all the samples, you put them all together in one, and then you calculated the sum of the squares of that entire population, okay? That's what the between means. So between means in between each individual item, and the sum of the squares within means within each column, okay? Again, you don't have to memorize this. You're not going to be quizzed on it. We're just trying to explain how this monster is built, okay? The degrees of freedom is pretty easy. That's the number of categories minus 1. So after you do all of this, it is going to do something called FDist, and it's going to take that F and your degrees of freedom, and it's going to give you an area. This is a p-value, okay? You take that p-value and you compare it to alpha, and you either reject or fail to reject the null hypothesis. And then you do your interpretation, okay? So here, got that, right? That was easy, right? No, it wasn't easy. The mathematics is very complicated. So let's look at an example. So this is actually old data. This data came from, I want to say, late 70s or maybe early 80s. So since this time, and by the way, this data is organized by cancer type and the number of days of survival after diagnosed with cancer, okay? So you have stomach cancer. So this individual was 124 days after diagnosis. That was the survival rate, okay? Bronchial cancer, colon cancer, ovary cancer, and breast cancer. And again, these were collected a long time ago, and advances in cancer research and cancer treatments have been spectacular over the last couple of years. And so these do not reflect current survival rates, okay? So just keep that in mind. Current survival rates are much longer than this, much longer. So kind of old data. I apologize for that. I got to get some new data. But what we want to do is we want to look at the mean number of days. So we're looking for mu, right? What is the mean number of days of the mean number of survival days of someone with stomach cancer? And what's the mean number of days of someone with bronchial cancer? And what's the mean number of days of someone with colon cancer? Our null hypothesis would be that all 5 of these are equal. That's the null hypothesis, that there's no difference in the average between these days, statistically speaking, okay? If we can reject that null hypothesis, then we will show that at least 2 of these have different mean values, okay? So that's where we're going with this. We've got 5 samples, and we want to compare them and say, are the means, is the average of these 5 samples the same? So here we go. We state our variables. Oh, and by the way, we're testing at the 1% level. So here are our 5 variables, and then we need to calculate the mean of all 5. So we're going to take the data and throw it into a Google Sheet. Here we go. And this is actually tech tool number 3. Okay, so if we take a look at tech tool number 3, here is the data. So we just copy and pasted this information in here. And then down here, this is where we found the count of items, how many items there are. Let's blow this up just a little bit for you. There we go. So here's the count. Here is the sum of the values, so you add them all up. Here's the sum of the squares of the values. This is the average, and this is the standard deviation. And again, you can see, and you're used to these formulas, right? Like STDEV and average for the average. So these are all pretty straightforward. Here's the sum of the squares. So that's that SUMSQ formula that I showed you earlier in the Google Sheet formula page. Here's the sum of the values. That's easy. And then here's the count. Okay, so just looking at row 22, just looking at this row, you can see that they're not all the same, right? Like these means are 286, 211, 457. So the means are all over the board. So we would expect that we're going to be able to reject this null hypothesis. That's kind of going into it, okay? So now that we've got this information, now we get into the calculation. And again, these calculations are going to be kind of done for you. So this is the number of between treatments and the degrees of freedom. So remember, we had 5 categories and we subtract 1. So the degrees of freedom is 1. The total number of categories that we had, if you take a look at the total number of items, 64 items, remember we said put them all together and as a one big set. So that number would be -1. So 64 minus 1 is 63, which means our within treatments have to be 59. You take the 63, you minus the 4, and you get 59. Okay, that's where that number comes from. Then what we do is we do the sum of the squares of the between of the 4. So we take these two, well, actually what we're going to do, this is the calculation. That's the calculation there. So what you're doing is you're taking the deviation squared of each individual data column and adding them up. That will give you the within treatments. Then you take the deviation squared of the entire population, and that will give you the total, and you subtract those two to find the in between or the between treatments. This is going to be done for you, right? Then you go to this and you divide this by this. So here's the division of those two, and then here's the division of these two. So that gives you your MS, which is SS divided by DF. And then finally, this is, you divide those two numbers, and that will give you your F score. That's your F distribution. You take that F score and you plug it into F dist along with the degrees of freedom of each one, and that will calculate the area under the curve. And so this is the number that we want, this area right here. And again, all you're going to have to do is copy and paste data into these columns, and these calculations are already set up for you. So you're not going to have to recreate these calculations. Let me show you another way. So here's a website, and this is called Social Statistics. And so you click on this, and look at that. Here are my 5 treatments. So I'm just going to go back to my tech tool, and I'm going to grab the data for the stomach cancer, and I'll zoom back just a little bit for this. I'm going to copy it, and I'm going to paste it right there. Then I'm going to highlight the bronchial cancer information, and we'll paste that. Then I'll do this, the 3rd column, we'll paste that. The 4th column, we'll paste that. And then the 5th column, paste that. So now I have all of my data in the website. The website does have limitations. For significance level, you only get to pick 1, 5, or 10%. Click 1%, and that's it. Now you just hit calculate. And when you scroll down, here is the summary of the data. So here are all those rows and columns that we had in the spreadsheet. Here they all are. So here's the number of items, the sum of the items, the mean of the items, the sum of the squares of the items, and the standard deviation of each one. And then this is where they calculated the in-between treatment, SS's, sum of squares, the within treatments, sum of squares, the degrees of freedom, the MS, the mean of the squares, this MS, the mean of the squares, and then the F value. So this is our test statistic. That's our F score, not the Z score, not the T score, not the chi-squared score, but the F score. And then you take that F score and they actually calculate the area under the curve, which is right down here. So they calculate the P value for this F score. And then because you told them the threshold was 1%, they tell you that the result is significant at P less than 0.01. So that means you get to reject the null hypothesis because our area came in under 1%. Now, again, the limitations of this are you're limited to 5 treatments. If you had 6 or more treatments, you could not use this website. If you had only 3 treatments, then you would only fill out this information, and maybe I want to change it to 5%. I can hit calculate, and it'll do the exact same calculations, but just for the 3 treatments. And here you can see that the results are not significant at the 5% threshold. So that means we don't get to reject the null hypothesis, which means the mean of these treatments at the 5% threshold, they are the same. They're close enough. And you're like, well, how could that be? Look at that 400. Yeah, but remember the threshold that you're checking. You're checking at the 5%. This website does pretty much everything that the tech tool does, but it does it kind of behind the scenes and just kind of gives you the answer. So choose your weapon. Which one do you want to use? Do you want, or use them both? Learn how to use them both. Let's finish this problem up. So here's all the stats that we looked at. Here is the website. And what I did is I grabbed screenshots of the website and put them here. So here's the summary of the data from the website that we looked at. And then here's the results of the data. And here's our F score. Okay. So taking all this into consideration, this is our F score. So we're going to take that and we're going to plug it into F distribution. And that's going to calculate the area, the same area that we had before. This is well less than our significance level. So we get to reject the null hypothesis. So we can say that we're going to reject the hypothesis that all the sample means are equal. And instead, we're going to replace it with our null hypothesis, which is that at least 2 of the means are not equal. And we kind of knew that going in, just looking at the numbers, you could kind of say that. So there's evidence to show this. And so the mean survival time for cancer is different than other means. And so that's kind of what we figured out. This course, don't forget, does not pursue a test to determine how much the means differ. All we did is we just said they're different, okay? There are additional tests that you could do, and you saw some of them on that website that actually go into more detail about, well, how far apart are the means, and is that significant? And so there's a number of these tests, the Duncan test, the Tukey test, the Schiffy test, tons and tons of different tests that advanced statistical students use. We're not going to use them in this class. So our purpose was to just give you a foundation of statistics so that way you can move on if you choose to. So the appropriate test is based on the type of experiment that you're doing and the precedent of the subject area. So as you advance in statistics, what you'll find is more reliance on statistical software packages. So some of the most popular ones are SPSS, which is Statistical Package for Social Sciences, SAS, Minitab, MathLab, and R. And R is actually one of the most popular statistical programs out there. And if you're interested in learning more about stats, we'll just do R stats. R is free. So it's called the R Project for Statistical Computing. And you can go and download R, download this program, and you can use this. A lot of companies use this to do their statistical calculations. Now, R is not very user-friendly. It doesn't have a GUI, a graphical user interface, and so everything is command line. Like you've got to type in command lines, and it's not that great. Remember back in January and February when we were in class looking at Data is Beautiful? And remember how every day we'd go in and we'd check on the growth rate of coronavirus and how fast it was growing in China, and we talked about exponential growth, and it just seemed like 10 years ago, doesn't it? Like that was just so long ago. But this is Data is Beautiful, and a lot of the graphs that you see in Data is Beautiful are built with R. Remember doing this back in January? Like towards the end of January and February, where we were looking at the exponential growth and monitoring this and watching the curves grow. And each day, every time we had class, we'd look at it and it was just kind of like, yep, it's growing, it's exponential. Okay, that's neat. Little did we realize the situation we would be in today, right? Like just amazing to think about that. Finally, we'll go to this. So again, this is an introductory stats course, and I hope that you learned something from it. I hope that you gain some appreciation for statistics and that you will become a more critical consumer of information. So you understand what margin of error means or what averages mean and the different ways that information can be presented and the mathematics, the underlying mathematics behind it. You know, what is a p-value? What does it mean to accept a hypothesis or reject a hypothesis at a 1% threshold or at a 5% threshold? What is a margin of error when the elections come around in, as we get into July and August and September, and you're looking at polls and they say, here's a poll number plus or minus 5%. You're going to kind of know what that means. There's a lot of applications in this. And so I hope we were able to convey some of that.